Okay, we're going to start Chapter 5 in Top Hat by talking about different types of stereoisomers. And so, if you remember back in a previous lecture, we outlined the different types of isomers, and a stereoisomer is going to be one where you have the two molecules that are the same structural or same constitutional isomer, but they differ in their three-dimensional shape. And the one that we're going to talk about first are what are called conformations. So if we look at an ethane molecule, C2H6, there's two ways that we can represent that. This structure showing the bold and dashed wedges in this tetrahedron, this is what's called a sawhorse representation. And remember, the bold positions are pointing towards you in front of the screen, and the dashed positions are basically away from you behind the screen. The positions that are on these regular bonds are basically in the plane of the paper or the plane of the screen. So this sawhorse representation would look like this molecule with the position towards you, which would be the bold wedge, and positions away from you, which would be the dashed wedge. So the first type of three-dimensional structure that we can, or three-dimensional stereoisomers that we can form, are by rotating around a carbon-carbon single bond. And those are going to be what we call conformations. So if we did that with this ethane molecule, we could basically begin to move these hydrogens closer together relative to each other. And in this case, this would be the representation where all those hydrogens are basically as close together as they can get. So different three-dimensional structures that can be formed by rotating around a carbon-carbon single bond are what are called conformations. Now, this ball and stick model would actually look like this as a sawhorse representation. These two bonds are in the plane of the screen. This position would be towards you. This one would be away. So we would have a bold wedge hydrogen towards you, a dashed wedge hydrogen away. This would be a bold wedge towards you. And this hydrogen in the back here would be on a dashed wedge away. Now, all of these hydrogens are actually lined up so that they are basically parallel to each other. These two, and the two in the back. Those are all going to be parallel to each other. Now, it's kind of hard to see that from this sawhorse representation or from this ball and stick. And so there's another representation that we commonly use to look down carbon-carbon bonds. And that is to take my big eyeball here and look down that carbon-carbon bond. Now, I'm actually back to the beginning structure that I showed you. And when we view this molecule down that carbon-carbon bond, it would look like this. This is what's called a Newman projection. And a Newman projection is named actually for Professor Newman, who I believe the older chemistry building at Ohio State is the Newman building. It's either the new or the old one. I think it's the older one. So they proposed that these Newman projections would be an easier way to see the orientation of these different groups that are attached in a carbon-carbon bond. So when I'm looking down this carbon-carbon bond, this is going to be my front carbon, and this is going to be my back carbon. And in theory, the back carbon is obscured by the front carbon. And so what I have is, I have hydrogens pointing towards me, which would be, if I wanted to call these like hydrogens A, B and C. This would be A. Over here, looking at it, B would be off to my left, which would be B, and C would be off to my right. And then on the back carbon, this hydrogen down here, we'll call that D. That hydrogen is all in the same plane of the screen, so D would be here. And then let's say E would be off to the left, and F over here would be off to the right. So this Newman projection makes it a little bit easier to see the orientations of the hydrogens relative to each other. So this is just a little bit different view, showing the front carbon in this purple color and then the other carbon in the back. Now, we don't have to draw a ball and stick. Instead, what we do is we draw a Newman projection so that it looks like this. So in a Newman projection with the position that's in the plane pointed up, we actually just draw kind of a 120 degree, 3 lines at 120 degrees away from each other. This intersection point represents the front carbon. And then to represent the back carbon, what I do is I just simply draw a circle, and then I show my hydrogens that are attached to the back carbon. And notice, so you can tell the front carbon from the back carbon on where the lines intersect. When they intersect, that's the front carbon. When they don't intersect, they're just in the ball here, in the circle, that is the back carbon. So this just shows you the back carbon in dark blue. Again, showing the hydrogens that are attached to the back carbon, but you don't see their intersection point because it's with the black carbon. So this is how we're going to draw Newman projections to analyze these different conformations of ethane and of other molecules as we work our way through this. So it turns out that there are 2 extreme conformations for ethane. Now, you could have any number of degrees of angles between those hydrogens, the hydrogen here on the front carbon and the hydrogen here on the back carbon, but there are 2 extremes. One is where the 2 hydrogens are as far away from each other as possible, and then the other where all of the hydrogens are basically parallel to each other or as close together as you can get them. So these 2 extremes have a name. The one that has the hydrogens as far away from each other as possible is called the staggered conformation. And the one where they're as close together as you can get is called the eclipsed conformation. And I have a question, and the video will come, we'll stop, and you can just give me your answer on this. Just as we start this, my question would be, which one of these do you think is more stable? The staggered or the eclipsed? And again, these are graded on participation, so if you read the book, you know the answer, or if you've had this before, maybe you know the answer, but I just want to get a feeling, what do you think is the most stable conformation here, the staggered or the eclipsed? So go ahead and answer that. Okay, well, let's take a look at this with what is called a space filling model, where we'll actually see the sizes of the hydrogen atoms. And I guess I don't show that. So let's just kind of take a tip here and look at this. So here's my staggered conformation. Here are my eclipsed conformation. So with these hydrogens as far away from each other as possible, that means, remember, atoms are just clouds of electron density. So we would want these clouds to be as far away from each other as possible, whereas in the eclipse conformation, they're going to be very close together. So the eclipse conformation is less stable, meaning that the staggered conformation is more stable. And if we make a space-filling model out of these, you can definitely see that the hydrogens in the eclipsed are really close together, whereas they're as far away from each other as possible in the staggered form. So staggered is more stable than eclipsed. Eclipsed is less stable than staggered. So now let's take a look at and try and draw the possible conformations for this molecule butane, which is going to be a little bit more complicated, but we'll go over how we're going to write a Newman projection. Now, number one, when I tell you, hey, I'd like you to write a Newman projection, the first thing I have to do is give you a molecule. And what I will oftentimes do is to give you the IUPAC name of the molecule, so you got to sketch it out. But then I also need to tell you what bond to look down. So in this case, we're going to look at butane, but we're going to look down the carbon-2, carbon-3 bond. So first we have to decide what's the front carbon and what's the back carbon. In this case, it really doesn't matter. We'll call this the front carbon. We'll call this the back carbon. So what I'd like to do is I'd like to sketch out the I'd like to sketch out a staggered conformation. And then I could come down here and I can sketch out an eclipsed conformation. So this is how we draw the staggered and the eclipsed conformations. So this is, again, this is staggered and this one is eclipsed. So now the question is, this is carbon-2, which was the front carbon. This is carbon-3. This is, again, carbon-2. This is carbon-3. So now in order to draw this structure, I need to look at carbon-2 and say, what is attached to carbon-2 here? Your first thing is carbon-3. Okay, yeah, carbon-2, the circle is carbon-3. So that's already taken into account. But what's attached to carbon-2? 2 hydrogens. So let's draw in 2 hydrogens, hydrogen and hydrogen. And then this entire group. And what's that entire group? It's a methyl group, so I'll go ahead and write in my methyl group. Okay. What's attached to the back carbon? Well, the front carbon. It's already built into the Newman projection. The back carbon has 2 hydrogens. Does it matter where I put the hydrogens? No. And what else does it have? It has a methyl group. Now it's important that whatever the other group is, if this was an ethyl group, you would want to show the entire group. The one thing that will get you into trouble is if you just write a carbon, no, write the entire group, and it'll be apparent why we do that in a few minutes. So here is my staggered conformation, one of my staggered conformations of butane looking down the carbon-2, carbon-3 bond. So is this the only one? No. There are 2 more. So what I would do is I'm going to write another blank Newman projection that is staggered, and I'm going to write a third Newman projection that is staggered. Now your choice. We need to keep one of the carbons, carbon-2 or carbon-3, front or back, in the same orientation, and then I'm going to rotate the back carbon. So what I like to do is I like to keep the front carbon, and this is just my preference. If you want to be different, you can do that. You'll be wrong, and I'm kidding. Everybody has their own system, right? Don't mess with my system, I won't mess with your system. So I keep the front carbon exactly the same, and now what I'm going to do is now I'm going to rotate the back carbon. Clockwise or counterclockwise, it doesn't matter. Let's go counterclockwise. So let's move this methyl group up here to that hydrogen position. So I'm going to rotate that methyl group to that position. At the same time, I'm going to rotate that hydrogen over here, and I'm going to rotate that hydrogen down here. So this is a second conformation staggered conformation of butane. Now, I can do that one more time by moving this methyl group, by rotating it to this position. That will rotate this hydrogen down here to this position and rotate this hydrogen up here to this position. So these are the three staggered conformations of butane. Now let's draw the three eclipse conformations, and then we'll come back and talk about all six of them together. So when I convert from my staggered to my eclipsed, notice that I'm going to rotate the back carbon not 120 degrees but only 60 to line up the groups. So what I again like to do is I like to put my front carbon in exactly the same orientation, and then then I would rotate this methyl group 60 degrees to put it in this position, this hydrogen 60 degrees to put it in this position, and this hydrogen then 60 degrees to put it in that position. So there is staggered, eclipse conformation number one. Then I'll draw the second and the third of the eclipsed conformations. So again, I keep the front carbon the same. And you might say, why do you have to keep one of the carbons the same and then rotate the other? And the simple reason is that way you'll generate all three possibilities. If you start rotating the front or the back, you could end up with the same structure. So choose one, keep it the same, and rotate the front or the back. And always rotate in the same direction each time. So now what I would do is now I take this methyl group and rotate it 120 degrees so that the methyl group goes there, this hydrogen down here, and the third hydrogen over here. So that would be eclipse conformation number two. Let's do it one more time. Let's take this methyl group, rotate it down there, rotate this hydrogen to this position, and we'll rotate that hydrogen up to that position. So now what I've done is I've generated three staggered and three eclipse conformations for butane, looking down the C2-C3 bond. Now once we do this, our next question is going to be, which one of these conformations is the most stable, which one is the least stable? But really what I'm going to do is I'm going to rank them. I'm going to rank them from number one, most stable, to number 2, 3, 4, 5, and number 6, which would be the least stable. And are there ties possible? Yes, there are ties possible. So now how are we going to rank the stabilities? Well, here's what I like to talk about. I like to talk about, for these Newman projections, interactions that are unstable. It's just easier to talk about, well, this molecule has these unstable interactions, and the molecule with the most unstable interactions is the least stable, and the one with the least number of unstable reactions interactions is the most stable. And there is no such thing as a favorable interaction. So I like to look at the ones that make the molecule unstable. Okay, rule number 1. All three staggareds are always more stable than all three eclipsed. So if I'm labeling these most to least stable, 1, 2, and 3 will come from the staggareds. 4, 5, and 6 will come from the eclipsed. Okay, I cannot think of an example where the least stable staggered is more unstable than the most stable eclipsed. And at this point I usually joke and I'll say, and when I find that problem, it'll be on the exam. But it doesn't happen that way. So number 1, number 2, and number 3 will come from the staggareds. Now, what is destabilizing? What's the unstable interaction or destabilizing interaction? The destabilizing interaction is when you have two non-hydrogen groups that are basically next to each other. And what I mean by that is one's on the front carbon and one's on the back carbon. So this is what is called gauche. So when you have two non-hydrogen groups next to each other, they are called gauche. The stable situation, and you have no choice, you have hydrogens that are gauche. So when you have non-hydrogen groups that are gauche, that is destabilizing. Why? We'll see the pictures in a minute or two, that these are large groups, and having large groups, which are nothing more than large clouds of electron density, when you have those getting close together, it destabilizes the molecule. Now, when we move to numbers 2 and 3 here, when we look at number 2, the two methyl groups are actually gauche to hydrogens. Well, they got to be gauche to something, so hydrogen's the best case scenario. And so in this case, the two methyl groups are not next to each other. This conformation and this terminology we would say those two methyl groups are anti to each other. Over here in number 3 here, the methyl groups are again gauche. Now, as far as stability, having the large groups away from each other is more stable than having groups gauche. And the bigger the groups that are gauche, the more unstable the conformation is. So in this case, having the methyl groups opposite each other or anti would be the number 1 most stable conformation. Now, as far as the other two go, they each have one methyl-methyl gauche interaction. Energetically, that's exactly the same. So these two would actually, I would call this number 2, and I would also call this one number 2 then, because they have the same energy. Now let me take a step back here. No, I said that, and I started to say it wrong. These two conformations have the same energy. They may not structurally be exactly the same, but they have the same energy. So the anti-conformation of butane is more stable than the gauche conformation of butane. Okay, so that would be numbers 1 and 2. If you wanted to say number 1, 2, and 3, and then say 2 and 3 are tied, I'm okay with that. Okay, now let's go to the eclipse conformations down here. Now with the eclipse conformation, what is destabilizing? The destabilizing interaction, number 1 is having the groups close together, like these two hydrogens, having them close together. But that's the best case scenario, is having two small groups like hydrogens next to each other, having them eclipsed. And that's the term we would say. We would say these two hydrogens are eclipsing each other. Well, that's baked into the fact that the eclipse conformations, even the most stable one, is still more unstable than the most unstable of the staggards. So the idea that all the groups are eclipsed makes the eclipse conformations number 3, 4, and 5, and 6. 4, 5, and 6. But in this case, we'll start with 3. What is really destabilizing? Having two non-hydrogen groups now eclipsing. Because, again, these are large groups. They're as close together as they can get. Those large groups mean negative charge. So I've got two clouds of negative charge really close together. So as far as these 3 eclipse conformations, this one would be the least stable of all of the conformations. These two are tied And so if I wanted to add numbers, I would say these two are number 3 and the least stable is number 4. The kinds of problems that you're going to get will probably have 1, 2, 3, 4, 5, and 6. They'll be unique energies. But in this case, we would say that the left and center conformations have the same energy. Okay, so that's how we evaluate the butane molecule and the butane conformations by writing Newman projections. And a Newman projection makes it much clearer as to the interacting groups that are anti or where they're not interacting, or gauche where they are, versus eclipse where they are. It's much easier to see this than it is in a sawhorse representation. So let's take a look at a couple pictures here. So looking at this, here is my gauche conformation, and here's my anti-conformation. Here are my sawhorse representations, basically, or ball and stick models. You can see that these two methyl groups right here are, you can see these two methyl groups are close together, whereas over here they're far away. You can see that better if we do a space filling model. And so in the space filling model, these two methyl groups are very close together, and they're far away over here. If you put these structures into a computer, into a calculation, you'll get that the anti-conformation is a little bit around a half a kilocalorie per mole, 0.6 kilocalories per mole, more stable than the gauche one. And we'll talk at some point a little bit about what does that mean in terms of energy, but it's fairly significant. Okay, that's a topic unto itself. Looking at the eclipse conformations, what do we have? We have when the two methyl groups are eclipsing each other, they are really close together in space, repelling each other, and they got to be eclipsed to something, so it's best to have a methyl group eclipsed to a hydrogen and vice versa. So actually, in this case, this methyl group and that hydrogen, and then this methyl group and that hydrogen would be the ones that are eclipsing. So it's a little bit harder to calculate the energies on these, but you can do it. So staggered, more stable than eclipsed. The non-hydrogen groups, when they are gauche or eclipsing, that makes the molecule less stable. So what we can do is we can kind of draw a diagram here, and every book has a slightly different version of this, where now what I'm going to do is now I'm going to rotate around one of the carbon-carbon bonds. So I'm going to rotate the back carbon with my methyl group. So if I start out staggered and anti, I'll call that 0 to 0 energy. And so if I then eclipse the hydrogens and the methyls, I go up to 4.3 kilocalories per mole, less stable, and more energy, less stable is the way it works. Then continue to rotate. So I'm going to rotate this methyl group up to make it now gauche to this methyl group. Well, that comes down and makes it 0.6 kilocalories per mole more unstable than the staggered, but it's much more stable than the eclipsed. And then if I try and eclipse both methyl groups, I go up to 6 kilocalories per mole, which this would be approximately 24 kilojoules per mole, 4.1 kilojoules per kilocalorie. So as we rotate around the carbon-carbon bond, we pay a price for forming more and less stable conformations. Now, I don't know if you remember, but in one of the previous videos, when we had sort of a sawhorse representation, I think I said that there was quote-unquote free rotation around the carbon-carbon bond. It isn't free. I have to pay an energy price for that. But at room temperature, you have somewhere in the neighborhood of 20-ish kilocalories per mole or so of energy in terms of thermal energy. So this molecule would actually be kind of rotating around because room temperature has enough energy to overcome all of these barriers. So that is how we draw Newman projections and how we analyze alkanes. Now, for our straight-chained alkanes, they tend to form this as zigzag structure. And the reason they tend to form zigzag structures as their most stable ones is simply because when you look down any of the carbon-carbon bonds, if you look down any of these carbon-carbon bonds, what you're going to see is in the zigzag structure, the methyl group, and in this case the ethyl group over here, are anti to each other. So straight-chained alkanes adopt the zigzag structure as their most stable conformation. Okay? So let's do one more problem in this lecture looking at the Newman projections for an alkane. So let me say this. Let's look at 2-methyl pentane, and let's look down the C2 C3 bond. Okay, so let's look down the C2 C3 bond of 2-methyl pentane. So the first thing we need to do to solve this problem is, and at this point I should say, if you're an overly ambitious go-getter student, which is my phrase, you could stop the video right now, do this problem, and see if you get it correct. Okay, so if you were an overly ambitious go-getter student, then I guess we'll see if you're right. If you were just waiting for me to continue on, that's fine. You can be overly ambitious in the future. So first thing we got to do is write the structure. So pentane means 1, 2, 3, 4, 5 carbons with a methyl group at carbon 2. So I'm going to go ahead and fill in my hydrogens here. So there is my 2-methyl pentane. I said look down the carbon 2, carbon 3 bond. So let's go ahead and do that. Now let's start by drawing out our 3 staggered blank conformations. And then let's go ahead and draw out 3 eclipsed conformations. Okay, so now let's do the same process that we did before. What's attached to carbon 2? Carbon 3. Okay, it's in here. A hydrogen and 2 methyl groups. So let's put a hydrogen and let's put in 2 methyl groups. Does it matter where those groups go? No. How about the back carbon, carbon 3? What's it have? It's got 2 hydrogens and an ethyl group. So hydrogen, hydrogen, and now let's write in the ethyl group. And I strongly encourage you to write out the entire structure of the ethyl group. Okay? So now we have our first staggered conformation. I like to again hold the front carbon in exactly the same orientation, and both in the staggereds and in the eclipsed. And For the staggered conformation, let's go ahead and rotate. This time we'll rotate clockwise, it doesn't matter. Let's rotate 120 degrees, so we put the ethyl group down here. That's going to move this hydrogen to this position, and it's going to move this hydrogen over here to this position. Now let's do that one more time. Take this ethyl group and move it here. Move this hydrogen over here. And then move this hydrogen down here. So there are my 3 staggered conformations. Now to go from the staggered conformation to the eclipsed, I have to move this ethyl group either clockwise or counterclockwise, but not 120 degrees, only 60. Let's bring it down 60, and uh-oh, what happened? So this is another mistake that you could potentially make. Notice that I did not carry my CH3 groups on the front over. So if you were yelling at the screen, which you'll probably do quite a bit, telling me to put that in, I now figured that out and put it in. So now let's bring that ethyl group down so that the ethyl group would go here. And then move this hydrogen over here and move this hydrogen to the top. And now we'll go ahead and rotate 120 degrees. So the ethyl group will come here. The hydrogen will go this way. And this hydrogen will come down here. And then one more rotation. Ethyl group to the top position. This hydrogen over here. And this hydrogen now down here. So there are my 3 staggered and 3 eclipse conformations. This is going to be A, this is going to be B, this is going to be C. This is going to be D, this is going to be E, and this is going to be F. Okay. So at this point, so now let's go through and let's analyze these and rank them according to from most stable down to least stable. So the first question that I'm going to ask is, before we go most and least stable, are there any of the 3 staggered conformations that have the same energy? Yes or no? Do any of these A, B, or C have the same energy? Yes or no? So the video will stop and it'll ask you yes or no. And if you said yes, you are correct. And so now my next question is going to be, what 2 letters have exactly the same energy? And so some choices will come up. Choose the set of letters that have exactly the same energy for the staggered conformation. Okay, and which letters were those? Well, let's analyze this. Let's analyze those 3. So what are the destabilizing or bad interactions? They are the Gauss interactions. So let's mark all the Gauss interactions that are destabilizing, and that's a symbol I use for looking at Gauss destabilizing interactions. Now, when we count up the number of, in order to determine stability, we need to count the number of destabilizing interactions. So A and C have 1 destabilizing interaction, and A and C did to have the same energy, and B has 2 Gauss interactions. So what we say is that we first look at the number of Gauss interactions. The smaller the number, the more stable the conformation. So in this case, the most stable is going to be A and C that have the same energy, and then the number 2, if this is number 1, the number 2 most stable conformation would be B, because it has 2 ethyl-methyl Gausses, Gauss interactions. Okay. So next, let's do the same thing for D, E, and F. Are there any 2 conformations of D, E, and F that have exactly the same energy? Yes or no? The answer is yes. And what letters have the same energies? So you could choose the letters that have the same energies. Okay, if you look at this, what are the destabilizing interactions in an eclipsed conformation? They are the eclipsing interactions. And so D and E each have 1 eclipsing interaction, and F has none. So that makes D and E the least stable, and it makes, so that would be number 4 in this case. Number 3, what is the second least stable, or what's a little bit more stable, would be F, that has no eclipsing interactions, but the fact is the ethyl group being eclipsed to hydrogens and the methyls make F less stable than any of the any of the staggards. So in terms of ranking these energies, we would have A and C the most stable, then B, then F, then D and E that have the same energy. Okay, so that's how we would analyze an alkane. If I give you the name and if I tell you what bond to look down, I will ask you to write all 3 staggards, all 3 eclipsed, and then rank them according to energy. The number of Gauss interactions for staggered destabilize the molecule, and the bigger the groups that are Gauss, the more unstable the interaction and the more unstable that conformation. Okay, so there's a couple of these problems where you're going to do this on the online quiz, and then you're going to do one of these problems and upload it as a written online quiz. Okay, so this is how we handle Newman projections, and this is a fundamental skill that we'll need in order to be able to look at energies. Okay, so that's the end of this video, and in the next video we will start looking at another set of alkanes and their energies, and that's going to be a cyclohexane molecule, and that's what we'll look at in the next lecture video. So I will see you then.